Hello and welcome to the AI Research Roundup. I'm Alex and today is May 9th, 2025. We are looking at a research paper from Hugging Face's trending list, published just 5 days ago, titled Learning Heterogeneous Mixture of Scene Experts for Large-Scale Neural Radiance Fields. This paper introduces Switch-NeRF++, a new framework for modeling enormous 3D scenes. It uses Neural Radiance Fields, which are methods for creating these detailed 3D views from 2D images. The system employs a heterogeneous mixture of hash experts. Think of it as a team of specialized subnetworks, each using hash grids with different resolutions to capture varying details, and a learnable, quote, gating network that intelligently directs parts of the scene to the best expert for the job. Alright, so this first figure really gives us a bird's eye view of what Switch-NeRF++ can achieve. We are looking at a massive urban scene spanning over 6.5 square kilometers from the Urban BIS dataset. On the left, you see the rendering from a method called INGP, and on the right, the result from Switch-NeRF++. The authors also provide a peak signal-to-noise ratio, or PSNR score, which is a common way to measure image reconstruction quality, where a higher score means the rendered image is closer to the real thing. Their method scores 20.76 compared to INGP's 19.58, and the zoomed-in details really highlight this superior rendering quality and scalability. Okay, building on those impressive visual results, this next figure really dives into the how. It contrasts the older Switch-NeRF framework with the new Switch-NeRF++. In the original, a 3D point undergoes positional encoding, which helps the model understand its location. Then, a gating network, a type of neural network called a multi-layer perceptron, or MLP, directs it to an expert subnetwork. The new Switch-NeRF++ uses a more efficient hash-based gating network and, crucially, heterogeneous hash experts. These experts use hash grids of varying resolutions, making the system much better at capturing diverse details across vast areas, contributing to those improved rendering results. So to really understand those heterogeneous hash experts, this figure illustrates their pyramid design. We see different experts, labeled Expert 0, Expert 4, and Expert 7, each specializing in a different grid resolution range. A grid resolution range. Well, it is essentially how finely or coarsely that particular expert is designed to look at details. For instance, Expert 0 uses a coarser grid, good for general shapes, while Expert 7 uses a much finer grid for intricate details. This layered approach is key to capturing the diverse data distributions, basically all the varied details in a large scene, which helps achieve that improved accuracy. Okay, moving to the results, this table lays out the benchmark performances on the NeRF dataset. We see several metrics, the peak signal-to-noise ratio, then structural similarity index measure, or SSIM. Another way to gauge image similarity, where higher is better, and learned perceptual image patch similarity, or LPIPS, which measures similarity like a human would, so lower values are preferred. Switch-NeRF++ not only achieves higher scores across these metrics for different scenes, but it does so with significantly reduced training time, for instance, achieving excellent results in just 5.5 hours with one configuration, showcasing the efficiency of its specialized expert design. Building on that efficiency, this next table gives us a closer look at performance on two other large datasets, Urban BIS, which we saw in the first figure, and Block-NeRF. Again, we are seeing comparisons using peak signal-to-noise ratio, structural similarity index measure, and learned perceptual image patch similarity. The table shows results for the original Switch-NeRF INGP and then Switch-NeRF++, using both homogeneous experts, where all experts are similar, and the heterogeneous experts with their varied grid resolutions. Across both datasets, Switch-NeRF++ with heterogeneous experts consistently achieves the best scores, highlighting the power of this specialized approach for superior rendering quality. Beyond just the quality, this next table focuses on a critical aspect, speed and memory efficiency. It compares rendering time and memory usage across NeRF, the original Switch-NeRF, and the new Switch-NeRF++. Look at these numbers. Switch-NeRF++ uses only 2,857 megabytes of memory and renders in just 6.65 seconds. This performance represents a massive improvement, a 16 times speed up compared to the original Switch-NeRF, and 13 times compared to NeRF, all while using far less memory. This really underscores the efficiency gains from the new architecture. So those speed and memory improvements are truly impressive. In conclusion, Switch-NeRF++ offers a highly scalable, accurate, and efficient way to model vast, real-world scenes. Its key innovations are learnable scene decomposition via the hash-based gating network and its heterogeneous mixture of hash experts, or HMOHE. This heterogeneous mixture of hash experts approach, it means specialized components tackle different detail levels, capturing scene diversity very well. This enables great novel view synthesis, creating new images from unseen angles. That is our roundup for today. Thanks for joining me, Alex. See you next time.